So what I'm going to do today is basically finish out this topic on beams and frames, and then next week we'll maybe have a couple of lectures on uh, just an overview of plates and shells, finite elements for plates and shells. And obviously, since I'm not testing you and all that, it's for your knowledge. So you should, in case, since you're here, that shows that you're interested in this. So, and I might go a little bit fast, but if there's something that's extremely pressing or something that's not clear to you, do stop me and let me know. Um, so just to briefly recount what we were doing yesterday or last time. So we started to talk about the finite element approximation for beams. So what we had done till that time was we had constructed this weak form exactly the same way. Take our three equations of equilibrium for axial force, bending moment, and the what else? And the transverse displacement. Rotations and displacements in the two directions. Those three equilibrium equations you take and you construct your weak form. And for the Timoshenko beam, we saw that all the derivatives in this weak form were of first order. So for Timoshenko beam, all the finite elements that we had developed for the first, for the one-dimensional problem, they're all valid. But then we also saw that if you take equal order approximations, then we have something called shear locking for Timoshenko beams only. So to get rid of shear locking, the common way is to use reduced integration for the shear term. So if you integrate this term just with one Gauss point, that will get rid of the shear locking. Another way to do that is use consistent interpolation. So what that means is that for the transverse displacement of the beam, that is W, you use a higher order shape function. And for theta, you still use a linear. So when you take the derivative of W, that's W prime, that would become linear, and that would be the same order as theta. So that does not conflict with the order of for the order of curvature, and therefore it skewers shear locking also. So so these were the types of first order approximations for Timoshenko beams, and these work because all our derivatives are of the first are only first order. But we saw that for Bernoulli-Euler beams, last time we started this, for Bernoulli-Euler beams, our weak form contains second derivatives, which means that now we must choose shape functions that are not only that don't only have the continuous derivatives, but their second derivative has to be square integrable. So not only the function, but the function's derivative has to be continuous. So for example, what I was telling you last time was we'll consider these two problems. This one is a Bernoulli-Euler beam. This one is our old one-dimensional problem. And we'll see how we can construct shape functions for a Bernoulli-Euler beam using an analogy between these two. So the governing equation for Bernoulli-Euler beam is this. Let's say there are no applied moments. And this was our old one-dimensional equilibrium equation. So now if you remember, when we were talking about this as the solution, the way we constructed this was we said that we are going to assume that the displacement is linear within any element. So first of all, we took our domain and we divided it up into 4 elements. And now then we assume that the displacement is going to be linear within the element. And what that allows us to do is to write this approximation. This is very similar to the Ritz approximation, A0 plus A1 H1. And using this Ritz approximation, the finite element idea is that the value of the displacement at the node should be equal to the degree of freedom. So this U1 is the degree of freedom, this U2 is the degree of freedom at 2. If you just simply evaluate this expression, just plug in the value of value of this node. Let's say this is whatever 3 point something, this is 4 point something. When you plug this in into that, you will get that u1, the degree of freedom here, should be equal to that value. Similarly, u2, that's axial displacement, has to be equal to the same expression evaluated at the second node. So in all this, uh, if you use this formula or if you use this approximation, your job would be to find out what is A0 and A1. That is what we do in Ritz approximation. But if you use the finite element formulation, you can express these A0 and A1 in terms of the degrees of freedom. So these are the element degrees of freedom. If you just write these two equations in the matrix form, you get this. And now you can take this matrix on the other side and invert it to calculate what A0 and A1 would be. And then you plug that back in here, and that's how you generate the shape functions. That's how we also generated the shape functions for the triangular element. For the triangular element, we had 1, x1, y1, and so on. And we calculated what the coefficients would be, plugged them back into the expression for the displacement, and that's how we got n1, n2, n3. So the same idea holds here. We take this matrix, invert it, and that allows us to write A0 and A1 in terms of U1 and U2. So when you write that, when you write this expression, this displacement expression, when you write that in terms of degrees of freedom, you can write that out as our regular U is equal to N times D. So essentially what we have done is we've eliminated A0, A1 and found out what our N1 and N2 shape functions are. And these are the same old shape functions that we had for one dimension. N1 is just 1 minus x divided by L. X is going from 0 to L. That's the length of the element. And N2 is simply x over L. So you can plug those values in and see that those two shape functions go to 1 at their node and 0 at other nodes and so on. That's how we constructed that. But now we want to construct some shape function for the Bernoulli-Euler beam where the degrees of freedom are the displacement at node 1 and the rotation. This red line denotes the rotation at node 1. Similarly, displacement at node 2 and rotation at node 2. So there are 4 degrees of freedom for each node. And the conditions would be that since there are 4 parameters, the least order shape function that we would need is cubic. So A0, A1, A2, A3. A general cubic function. And its derivative for Bernoulli-Euler beams, we know that theta is equal to W prime. There's no shear displacement. So you just take the derivative of this, that's right here. So using these two relationships, you can calculate what would be the displacement at this node and the rotation at this node, and the displacement at this node and the rotation at this node. So essentially that's what I have here. W1 theta 1, W2 theta 2, where theta 1 and theta 2 are nothing but W prime. So you get 4 equations. And you have 4 unknowns, which are A0, A1, A2, A3. So once again, you can write that out into a matrix form, invert the matrix, take it to the other side. You get your values of A0, A1 in terms of the degrees of freedom now. So those A1, A0, all these A0, A1, A2, and A3, they were Ritz functions. But now our degrees of freedom are W1 theta 1, W2 theta 2. So the objective for all finite element shape functions is to try to express this kind of a formula in terms of the degrees of freedom. So once you do that, you get these types of, the same type of function that you had N times D. This is shape function matrix times degrees of freedom for the element. And these 4 shape functions, what they look like is what I've drawn here. So this is N1 and N3. N1 and N3, which correspond to W1 and W2. And if you remember, maybe if you've taken matrix structure analysis, this is exactly how we constructed the element stiffness matrix back then. So you give a unit displacement, find out the forces and moments required to give that displacement, and that's how you constructed element stiffness matrix. But this is where it actually comes from. There are obviously a lot of other different ways also to construct polynomials, which would be continuous at the nodes, and their derivative would be continuous at the nodes. So so you can see that n1 and n3, these are n1 and n3. If you sum them up, their sum is actually equal to 1. These four terms cancel off, and their sum is 1. But these two functions, they correspond to theta 1 and theta 2. So they do not sum to 1. So this is just a peculiarity of these cubic shape functions that we use for Bernoulli-Euler beams. But the idea is the same, and how you construct n1, n2, n3 is exactly how you constructed n1 and n2 for one dimensions, and even for the triangular element, this is exactly the same procedure. So one thing to note here is that these types of functions, they are called Hermite functions. And the other class of functions that we had learnt about was Lagrange shape functions. And if you remember, the Lagrange shape functions were functions which go to 1 at that node and go to 0 at other nodes. But when you connect them, their derivatives may or may not be continuous. So for example, these are Lagrange shape functions. These are Lagrange shape functions of linear order. When you connect them, they will form that hat shape functions where their derivative would not be continuous at the nodes. On the other hand, these Hermite functions, they have this property that not only the function will be continuous, but its derivative will also be continuous. So primary variable and derivative both are continuous for Hermite cubic shape functions. Those are the shape functions we use for Bernoulli-Euler beams. So after that, it's pretty straightforward. Once we have our finite element approximation that u is equal to n times d, you just take that u is equal to n times d, plug it back into the weak form, and now I've divided the weak form into a number of elements. So for example, in this case, the problem that I was trying to solve was this cantilever beam problem. I've taken this entire domain, divided up into any number of elements that you want, and I'm going to sum the weak form over all these elements. So summing up this weak form over all the elements, you substitute in your u is equal to, so in this weak form, I'm actually including the axial term also. So if you remember, this was the term that came from bending, and this is the term that comes from axial contribution of the internal work. So now you just substitute your u is equal to nd in both of these equations, and your element degrees of freedom would become u1, u2. Those are the axial displacements, w1 theta 1, w2 theta 2. So for the two nodes, you have all these 3 degrees of freedom. So each node has 3 degrees of freedom. And what this leads to is our same old familiar equation, kd minus f. After that, you can assemble that and all that, enforce boundary conditions, and solve for it. So for Bernoulli-Euler beams, I think we talked about this a little bit last time, maybe. The structure of the element stiffness matrix. So this term is what contributes to the element stiffness matrix. You are summing up the weak form over elements. If you calculate this will give you the same old axial stiffness matrix that you had before. This term, now W has 4 shape functions. So this term is what gives you the bending stiffness matrix. So here's the question. What is the size of KUU? It's right on the next line, 2 cross 2. That's the I guess drawback of writing up everything beforehand. So and similarly, you have KWW. Since there are 4 shape functions, the bending stiffness matrix is 4 cross 4. So when you assemble them, the total stiffness matrix would be 6 cross 6, which is basically 3 degrees of freedom per node for each element. So that's why we have the element stiffness matrix as 6 cross 6. And this, hopefully, many of you should be familiar with. So this is the same stiffness matrix from the way we constructed long back, I guess, you give a unit displacement, and the forces that are required to hold that displacement is 12 EI over L cube. That's right here, those two forces. And the moments that are required so that there's no rotation at the nodes are 6 EI over L square. So those are right here. And if you sum up the moments for this, 12 EI over L cube multiplied by the length of the element, that's the total moment due to the forces, and that exactly cancels off this 6 and 6. So, so this one column is in force equilibrium and in moment equilibrium. And if you remember, when we constructed the element stiffness matrices for triangular element or Q4 element, the sum of any row or any column should be 0. But since this is a bending element, the two components of the forces, plus 12 and minus 12, they cancel out. And the moment is 12 EI over L cube multiplied by L minus 6 and minus 6. So that's also cancels out. So that's also 0, meaning it's in equilibrium. So you can verify also for the other columns by just giving a unit displacement or rotation for the degrees of freedom according to that. Element force vector is also similar, but this is a little bit different than our than the Timoshenko beam. In the Timoshenko beam, we were treating N, Q, and M separately. So we had a 3-column vector. If you turn back the pages, you can maybe take a look. There were 3 forces or applied forces in the Timoshenko beam. In this case, since transverse and bending is coupled, the element force vector is calculated like this, and these are the transverse bending contribution. These are the axial contribution. So this vector turns out to be 6 cross 1, just like it should be, because there are 3 degrees of freedom per node. So after this, now you know how to construct the element stiffness matrix, how to construct the element force vector. After that, you just have to assemble it, and you get this global equation. You solve for all the degrees of freedom for the global problem, and then the post-processing is pretty much plotting the deformed shape. Plotting the deformed shape and plotting maybe what is the axial force, shear force, and bending moment along the length of the beams. But here is a little bit of a thing that you should keep in mind. So when you are plotting the deformed shape, if it's a Timoshenko beam with linear elements, in that case, your nodes or the displacement between the nodes is going to be a straight line. But in addition to those, you also have the cross section, the orientation of the cross section that is denoted by this theta. And remember that for Timoshenko beam, this theta 1 and theta 2, they are independent of W1 and W2. So that's why even if you have, let's say this is a Timoshenko beam element, after deformation it goes to some place like this. If it's a Timoshenko beam, the cross section can be oriented in any direction independent of that that W. So that's why you have you draw a straight line between those two nodes, and we usually depict the cross section with an independent orientation to denote where is the cross section. But on the other hand, Bernoulli-Euler beams, here the W1 and W2, when you draw that, their W1 and W2 they are interpolated with cubic shape functions. So you cannot connect them with a straight line. I mean, you can approximately display them connecting with a straight line, but ideally what you should do is display it using the shape functions, those 4 shape functions that we talked about. That's how you would display the deformed shape or plot the deformed shape. And in this case, this cross section, W1 prime is dependent on W1. You just take the derivative of that, the cross section always remains normal to the beam axis. So, so that's how you would plot the deformed shapes for the beam elements. And after that, once you know the axial displacement at any point along the length and the transverse displacement W and theta at all the locations, you can calculate shear force. That for the Timoshenko beam is given by this. For the Bernoulli-Euler beam, it is minus EI W triple prime. For bending moment at any location along the beam, we just have EI times curvature. And curvature, the exact formula again is theta prime. But when you use Bernoulli-Euler beams, theta prime is nothing but W double prime. So once you have the final solution, D, you can just go back and find out what the element degrees of freedom are, plot the shape, and calculate shear force and bending moment at any location you want. And using those shear force and bending moments, then you can go back and design that cross section to be able to carry that shear force and bending moment. So this is basically how we construct finite element approximations for Timoshenko beams and for Bernoulli-Euler beams. And the next topic that we have here is frame structures. So the idea is that now you know how to calculate how to calculate the response of one beam element. But obviously, in real life, all our structures are made up of beams and elements. And this is an example of a 3D frame structure. This is a 2D frame. So the idea is that you should be able to divide this structure into one or more beam elements. So for example, this part of the element here, this part of the structure, I'm dividing it by using 2 elements. I could use 5 elements, 10 elements, and depending upon what is the applied load and all that, you could have a this is just like our convergence study that we did for our cantilever beam. You have to use enough number of beam elements along the length of each of those components so that you get an accurate enough response. So in order to solve these types of problems, what you need to do is to calculate the element stiffness matrices for each one of those elements. But then obviously you cannot just assemble them straight away. So what you need to do is something that we did for our 3-dimensional and 2-dimensional truss problems. Yes, question? No, so these are nodes. These are finite element nodes. So you could have 2 elements, 5 elements, whatever. You can also have 1 element, but that may or may not give you a good accurate response. So in general, each one of those columns or beams you would further subdivide with multiple beam elements, and that is not something that we do in traditional structural analysis, but it is better to have more beam and column elements along the length. So in order to solve these types of problems, you would have to assemble these equations, and since what we have right now is an element stiffness matrix in the local coordinates. So this is also something similar to our truss problem that we did. We constructed our 1D truss element that was just EA by L plus 1 minus 1. In this case, we have a 6 cross 6 element stiffness matrix in the local coordinates. We need to transform that to a 6 cross 6 element stiffness matrix in the global coordinates. So it's element stiffness matrix in the local coordinates to the global coordinates. And that transformation is the same way that we did for the truss elements. We have 3 degrees of freedom per node. And if you want to transform these 3 degrees of freedom, which is U1, W1, theta 1, to X1, Y1, and theta 1, what you have is the regular good old transformation matrix of cosine and sines. In 2 dimensions, it is not that problematic. So using this matrix, you can transform the degrees of freedom from node 1 to degrees of freedom in the global coordinates at node 1. And using this matrix, this transforms the degrees of freedom from node 2 to the global degrees of freedom from node 2. And you do that for each and every element, meaning, for example, in this case, you have all these elements. They all have a different theta. So theta for this element is different from theta for this element. So you transform every element into the global coordinates. And once you've done that, now you can add these degrees or assemble these degrees of freedom. So usually if you denote this matrix with a T transformation matrix and write out the weak form same as before. The weak form actually does not change because this is a scalar. It does not depend upon any direction. So the weak form is exactly the same weak form that we had before for Bernoulli-Euler beams. There is a sum over elements of virtual displacements times kd minus f element wise. Now this kd and all that, they are in local coordinates. That's the superscript L. So what you would do is, okay, so which one is global coordinates and local coordinates? What would be, this is d element degrees of freedom in the local coordinates, this vector right here, and this vector right here, this is d element degrees of freedom in the global coordinates. So you can see that if you write this out, then d element degrees of freedom in the local coordinates can be expressed as T transpose times element degrees of freedom in the global coordinates. So essentially what I'm doing is just taking T to the other side, it becomes transpose, and now I'm substituting for D element using this formula right here. So this D is T transpose times D, this D is T transpose times D, this F is T transpose times F. And all that I will do now is you have this vector. If you transpose that, what you would get is D global transpose, and this comes inside. So this becomes a transpose and comes inside, and you have T times K times T transpose. This is how you transform an element stiffness matrix from the local coordinates to the global coordinates. And this T times this T transpose cancels off. That's identity, so that's why we don't have anything here. And now if you denote this matrix with a global, so this is the element stiffness matrix in the global coordinates. And if you denote that with Kg, now you can assemble all these things. So note that the summation, this was sum over all the elements, that summation has changed to assembly over all the elements. So once you do that, you get the same equation, and now you can solve for this D using boundary conditions. So the essential point here is that to be able to assemble these element stiffness matrices, that matrix that I gave you on the previous page, 6 cross 6 or 4 cross 4, you need to transform that to the global coordinates. And in 2D, that transformation to the global coordinates is fairly straightforward. Once you do that, you can transform your element stiffness matrix to the global, and your force vector, element force vector to the global force vector, and just assemble and solve. So this 2D problem is not that difficult, but in 3D things become a little more interesting. So let's take a look at this. So all that theory that we had developed for Timoshenko beam and for Bernoulli-Euler beam theory and all that, that was planar beams. And if you remember when we were setting up that planar beam, we said that our actual beam is in 3 dimensions. So this is x1, x3, and x2. What we chose to look at was x1 and x3. So the axial displacement we chose was along x3, that was equal to w3 in the 3-dimensional case. The transverse displacement, w, was equal to w1, and theta was equal to theta 2. So that's rotation about the y2 axis, or x2 or y axis. So you can see there is a mix of all three coordinates even in the planar beam problem. So in the planar beam problem, w3 is displacement along the axis, w1 is the transverse displacement, theta 2 is the bending of the, or the rotation of each of those cross sections. And similar relationships hold for if you want to study bending in the x2 and x3 direction. So this is bending in the x1, x3 plane. If you are doing bending in the x2, x3 plane, you will have different axial and transverse and rotation variables. So another point to make here is that when you have small displacements and small rotations, the bending in the two planes is decoupled. So, for example, in this case, the three-dimensional frame case, you have let's say this I-beam which is oriented along x3 direction. Its major principal axis is about x1, and the weak axis or minor principal axis is along x2. If the displacements and rotations are small, you can decouple both of them and treat them independently. But as soon as you get into large displacements, large rotations, all this theory breaks down, and there is a much more advanced theory of geometrically exact beams that you would have to resort to. But in civil engineering and structural analysis, I don't think there's even a handful of people in the world that do that anymore. But if you have small displacements, this is fine. But if you're studying something like progressive collapse, you have to use a large displacement beam theory. So if you think about it, this is a little bit weird. If you think that the bending in the two directions is independent. If you're bending in the x1, x3 plane, you're saying that the beam deforms like this, but in the other direction, in this direction, it has not deformed at all. So that can cause actually some discrepancy between where the cross section is, and that can lead to some trouble. But so the idea is that if they are decoupled, then what we can do is set up the element stiffness matrix in 3 dimensions first. So let's consider this beam element that's going from node 1 to node 2, and now each one of those nodes has 6 degrees of freedom. So you have this displacements in 1, 2, and 3. Those are W1, W2, W3. In addition to that, you have rotations. So theta 1, what does that theta 1 correspond to in terms of, is that a bending? That theta 1 corresponds to a bending rotation in the x2, x3 plane. So theta 1 is the bending in the x2, x3 plane. This theta 2, this is like you're using with your right hand rule. If you choose theta 2, that implies bending in the x1, x3 plane. Similarly, theta 3, what is that? Torsion. So theta 3 is torsion along the axis of the beam. So what you could do is you could set up the equation for, or set up the element stiffness matrix for this element using either Timoshenko beam or Bernoulli-Euler beam. So here what I'm showing you is the Bernoulli-Euler beam. If it is in x1, x3, we had this equation before, or we had this stiffness matrix before, and this is connecting W1 with this W1, and theta 2 with this theta 2. So this is W1, theta 2, W1, theta 2 for the 4 columns and the 4 rows. So again, the degrees of freedom for this x1, x3 plane are W1 for the transverse displacement, theta 2 for the bending rotation. And for bending in the x2, x3 plane, this plane, the transverse displacement is W2. So this row corresponds to W2. This column corresponds to theta 1 or minus theta 1. So now that you have these two stiffness matrices for the bending contributions, you also need stiffness matrices for the axial contribution, that is relating this W3 with this W3. The axial displacement along from node 1 to node 2. And that's our same old stiffness matrix. For the torsion, we have rotation, the torsional rotation at this node versus torsional rotation at this node, and that matrix is also very similar. Instead of EA over L, we have GJ over L, where J is the polar moment of inertia. So you can see also that the polar moment of inertia is the sum of two principal moments of inertia, Ix plus Iy. And for bending in the x1, x3 plane, we have this Iy, which is governing, which is the major Iy. And for bending in the x2, x3 plane, we have the minor axis. So this is Ix that would be governing for x2, x3 plane. Yeah, question? Mm-hmm.
But if we have to say approximate using a shape function and get these elements, what would be the order of approximation to get these exact elements?
So these are the Bernoulli-Euler beam stiffness matrices that we just talked about using the Hermite cubic shape functions. Instead of Bernoulli-Euler beam theory, if you were using Timoshenko beam theory, then all those terms would be different. But you can still assemble them. You can treat the bending in these two planes differently, as in decoupled. And then all that you need to do is to assemble or place these values in the 12 cross 12 stiffness matrix. So now this is a three-dimensional beam element. It has 6 degrees of freedom per node. The total degrees of freedom per element is 12. So that's what I'm showing you here. So the idea is that you would write this weak form, which is sum over all the elements of the same old thing. And this weak form is governing the behavior of this kind of a three-dimensional frame structure. So divide your three-dimensional frame structure into as many number of elements as you want, and now you are summing up your weak form along the lengths of each one of those elements. So for each one of those elements, you are trying to construct this local stiffness matrix. And this local stiffness matrix is pretty much an assembly of this 4 by 4, this 4 by 4, this 2 by 2, and this 2 cross 2. You just have to place them in the right locations. So what degrees of freedom are associated with, let's say, this ky? Can somebody tell me what is the degree of freedom here? This is ky is the bending in x1, x3 plane. So what is the degree of freedom that I should write here? This is relating W1, theta 1. This is W1, or sorry, theta 2. And theta 2. So this is from node 2. This is from node 1. And the same thing for the columns. So this is W1 theta 1 from node 1, and this column is W1 from theta W1 and theta 2 from node 2. And if you look at the final positions of these numbers in the 12 cross 12, all I've done is that those 4 numbers are here, 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 and here. And that row corresponds to node 1 W1. That row, this brown numbers, these are node 1 theta 2. This is node 2 W1. This is node 2 theta 2. So essentially what we have done is we've taken that 4 cross 4 and just placed those numbers in those correct locations. So similarly, we do the same thing for this matrix. What are the degrees of freedom for this? What is the first row? W2 and theta 1. This is node 1, W2, theta 1 for node 2. And once again, if you take a look at the 12 cross 12, this green row went to W2. That's right here. W2 at node 1. theta 1 at node 1, W2 at node 2, theta 2 or theta 1 at node 2. So essentially, after you've done the bending terms, these are the 4 axial terms. Those axial terms are relating the axial displacement at node 1 in the 3 direction, node 2 in the 3 direction, with node 1 and 2 in the 3 direction. And similarly, the red terms here, they correspond to the torsion. So you have theta 3, theta 1 at 3, theta 2 at 3. Those are the torsional terms. Everything else is 0. So that's how you construct a stiffness matrix for a 3D frame element. Each node has 6 degrees of freedom, so the size is 12 cross 12. Everything, all the 2 bending directions are decoupled, so that allows us to write this type of a matrix for a 3-dimensional frame element. But this is again only in the local axis. So if this beam is arbitrarily oriented along in space, then we have to further transform it. So that's the next step for 3-dimensional frame analyses. This was the beam element that we were just talking about. It has these local degrees of freedom W1, W2, W3 that we have just set up. And we want to now transform those local degrees of freedom W1, W2, W3 into these global degrees of freedom. And in order to do that, essentially what we are trying to do is rotate our triad from the local to the global axis. And this is also something that we did long back in chapter 1 when we were talking about tensors and change of coordinate system. So instead of that cosine sine matrix, that simple matrix, in this case we have a little more complicated matrix. So what this matrix does is takes the degrees of freedom from W1, W2, W3 to this Wx, Y, and Z. You take this matrix, or operate upon these degrees of freedom, and that would give you the global degrees of freedom. And the components of this Q matrix, they are, all these components are nothing but the direction cosines. So for example, let's say this is 1, 2, 3, and then we have let's say X, Y, and Z. So the angle between 1 and X, that, let's say that angle is theta 1x. So this Q11 is actually equal to cosine of theta 1x. And similarly, if you measure all the angles between 1 and, let's say, y, 1 and z, you will have theta 1y, theta 1z, and so on. And the easier way to see that is right here. Let's say you have these unit vectors along all these 3 triads, L1, L2, L3 in the local coordinate system, G1, G2, G3 in the global coordinate system. If you just take the dot product of G1, that's this G1 with L1, this L1, that would be nothing but cosine of theta 1x. Does that make sense? So if you take dot product of L1 with G1, that's cosine of this theta 1x, and that's equal to Q11. That's how you construct a transformation matrix from, in 3 dimensions, from one system of coordinates to this another system of coordinates. And now we can use that to construct the transformation matrix for this 3-dimensional frame element. If you remember what we just did right now for 2-dimensional frame element, this was our transformation matrix T. Just have Q and Q here, and these 3 degrees of freedom go here, these 3 degrees of freedom go here. But for 3-dimensional cases, you will have Q, 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 So that transforms these first W3 to these W3, and these theta 1s all to theta x. So this is how you would transform the degrees of freedom from the local axes to the global coordinates. And after that, you use the same sort of idea. You're writing the weak form, transform them to the global coordinates, and that sum then turns into assembly, and you get your equation just like before. So you can solve this equation with boundary conditions and see how that goes. So that's pretty much on the theoretical side. Let me just quickly take a abacus example, and maybe you guys have already seen this. So in abacus, basically, if you want to make a three-dimensional frame, this is something that you can do fairly quickly. In the part module, you go and sketch out your three-dimensional structure with a wire. In the property module, what I've done is defined a steel material. And then in the section module, when you create the section, you're saying that instead of that solid section, you would use a beam section. And in this case, you can choose the profile. Profile is like the cross section of the beam, so something like I-beam. So you can define all these values for the cross section of the beam, and I've done all that. So let me dismiss this. And then you assign these the section to each one of those elements. And further, I think what you need to do is actually do this, assign a beam orientation. So in three-dimensional frames, what abacus has no way of knowing which is the major axis, which is the minor axis. So this is the beam element that you've just drawn, something like this. You have to define which is the major axis and which is the minor axis. So for three-dimensional frames, that's the special thing that you need to keep in mind. Another thing here is in part display options, if you say render beam profiles, so it pretty much shows you what type of profile you have chosen. So let me zoom in here a little bit. So you can see that these are I-beams, that those wires, they actually represent I-beams. And but that representation is only for graphics. All that calculation, for the calculation purposes, abacus is just treating it like one beam, one-dimensional beam element. So finally, I think if you go to the load module and all that, this is the load sets that I defined for the 6 nodes at the bottom. They are fixed against rotation and displacement. You apply some gravity loads and you apply some, let's say, wind or lateral loads. And if you try to run and see what the results are, you can plot the deformed shape and all the stresses. And so the deformed shape is this. Let's see. Right. So this is the deformed shape of the structure. Basically, it was here. This is the original position. This is the deformed position under those loads, and you can go and find out what is the section force, which is actually the shear force of at any location within the beam, section moment, which is bending moment at any location in the beam, and then you can use that to design your structure, individual beams and columns. So so yeah, usually it's not that difficult to, and you can see all these individual beam elements right here. So in this case, I've used 5 beam elements along the length of the beam. All right, so maybe we should stop here, and next week we'll just do a couple of lectures on plates and shells, and then we'll be done for the class. Okay. Also, some of you have actually not turned in your progress reports. So please do that before the weekend. And next week, anytime, you can start submitting your final reports also. I'll set up something on Blackboard so that you can submit an electronic version of your final report and maybe any CAE files that you have. So, all right. So see you guys on Monday. Yeah.